Before we proceed to the domain and range of exponential function, we need to understand again how to determine exponential functions. Well, the first thing you need to do, you need to observe the base. That when the base is greater than 0, then that is considered to be one of the conditions. You also need to observe that there is an exponent which is a variable. So here, f of x is equal to 2 raised to x has a base that is 2, which is greater than 0, and there is a variable x which is the exponent, and we consider this function f as an exponential function. Observe function g. We see a base that is -7 because that is enclosed, okay? -7 is not greater than 0, then this function g is not considered as exponential function. Now, function h of x is equal to 0.003 x squared plus 1. You see, x is not an exponent in this case. And as you observe, it is a polynomial function of degree 2. So this one is a quadratic function. Okay? This is not an exponential function. Observing function p, which is p of x is equal to 1 over x, the quantity raised to x squared minus 1, the base is greater than 0, and the exponent, there is a variable here, x squared minus 1. We consider function p as an exponential function. The domain and range of exponential functions are very crucial in understanding the real values, okay? Take note that we just need to understand that the domain of exponential function is the set of all real numbers. So in interval notation, we have this. Okay? We can enjoy all real numbers because all these numbers can provide function f a real value on its range. Okay? Now, the range of exponential functions vary. Meaning to say, you need to understand how the function behave. We need to understand that f of x equals to a raised to x. From f of x that is equal to a raised to x, that is the representation of exponential function, a here should not be 1 and a must be greater than 0 but not 1. Okay, so because of that, we have two possible cases. That is when a is between 0 and 1 and a is greater than 1. Okay, it is simply suggested that when the variable x here from this case keeps on increasing, okay, then the value of y, which is f of x, just like this. If we have an example that is f of x is equal to 1/2, then raise that to x. Take note that 1/2 can also be represented into 2 raised to -1. Okay, and the rule of the exponent will tell you that you need to multiply -1 to x, so you have 2 raised to -x. These two are the same. So what will happen if you keep on increasing x here? It is now observed that, okay, let's have a tabulation. If x is 0 here, so 2 raised to, well, there's no -0. 2 raised to 0 is simply 1. But when x is equal to 2, you have 2 raised to -2, which is now equal to 1/4. When x is equal to 3, we have 2 raised to -3 here, which is equal to 1 over 2 raised to 3, and that is equal to 1 over 8. Now you try to observe. I am increasing the values of x here. From 0, I move to 2, then move to 3. But what happens to y? It decreases. From 1, it turned to 1/4, to 1 over 8. That is a justification that when the base, okay, take note, this is a proper representation that when the base is between 0 or 1, then as x keeps on increasing, y keeps on decreasing. To show the behavior of f of x that is equal to 1/2 raised to x, we are going to graph it, okay? So here, we know that when x is equal to 0, then f of 0 will give us 1. So If x is 0, we place 0 here, okay? Because the numbers that will be placed on the left are decreasing and the numbers on the right are increasing. So 1/2, the quantity raised to 0 is simply 1, okay? And when x is negative 1, so we have f of negative 1 is equal to 1/2. We raise that to negative 1, will give you 2 raised to negative 1, raised to negative 1. I'm just applying the rule of exponent, okay? And that is equal to 2. So you see, if this is negative 1, it will immediately provide you 2. Okay? So, when x is 0, f of 0 will give you 1. And that is automatic, okay? When x is 1, it will give you 1/2. Okay? So, when x is 2, so 1/2 times 1/2 is 1/4. But when x is negative 1, you see here, f of negative 1 is equal to 1/2 raised to negative 1. 1/2 is 2 raised to negative 1. I'm just using the exponents for you to observe relationship, okay? Negative 1 times negative 1 is 1. So that is immediately 2. Okay? So I place this one 2. If x is negative 2, then f of negative 2 will immediately be 4. You see? 2 and this is 1/2. So the reciprocal of 1, 1/2 is the answer when x is negative 1. So I'm now plotting it. If this is negative 2, it will give us 4. And if this is 1, it gives us 1/2. So somewhere here. If this is 2, 1/4. Now I will connect the points and show to you the graph of f of x that is equal to 1/2 raised to x. Okay? The graph is a curve. So this one is extended to infinity. Now here you are observing that the trend of the graph is that it's just lying on the x-axis. The reason here is f of x will never be equal to 0 because no value of x can give, okay, f of x 0. So in this representation, y that is equal to f of x will just keep on approaching 0 as x approaches positive infinity. It is also observed here, from 1/8 it will also decrease and decrease, but will not be 0. It just keeps on approaching 0, but will never be 0 and will never be a negative number, okay? So on the graph here, we can say that there exists what we call a horizontal asymptote. We have what we call a horizontal asymptote here. The reason here is this line or the x-axis, which has an equation y is equal to 0, remains to be a line where the graph keeps on lying on this particular line. So that is an asymptote, okay? We also observe that the trend of the graph here, y keeps on increasing. The value of y keeps on increasing while x keeps on decreasing. That is why here it moves on the left part. So the behavior of this is, as you keep on increasing values of x, y keeps on increasing. That is inversely proportional, okay? But in here, as you keep on increasing x here, we keep on increasing x here, the value of y just keep on approaching, getting closer and closer to 0. Okay? Now, domain is still the set of all real numbers because we observe here negative infinity, positive infinity. But how do we describe the range of this kind of function f? The domain is still the set of all real numbers, but the range will now vary. If we observe the graph, the y here, f of x, will never be 0, will never be a negative number, but will always be. So we have the horizontal asymptote, y is equal to 0, and the value of f of x here will never be a negative number, will never be 0 as well. So meaning to say, the values of y are the set of all positive real numbers, or in interval notation, we have all numbers greater than 0. That is also justified on the behavior of the graph, that y keeps on increasing, but when it goes down, will just keep on approaching 0, but will never be 0. domain is a set of all real numbers, and the range is a set of all positive real numbers for f of x that is equal to 1/2 raised to x. So we can say that, what if you try to add 2? So if this 1/2 raised to x will never be 0, or the range will now be all positive real numbers, or we have this interval notation, what if you add 2? So it means to say 0 plus 2 will give you 2. But 2 is not a possible value of y. Why? Because this is never be 0. It is just greater than 0. So when a number greater than 0 is added to 2, then the number is greater than 2. That is why the range is all numbers greater than 2. Okay, that includes up to positive infinity. But when you subtract negative 3, this negative 3 here will never be a possible value of y, and it means to say that will increase from negative 3 and it goes to positive infinity. Remember that the domain is a set of all real numbers, and the range will be very relevant for us to determine the horizontal asymptote. Just look into this 0, okay, this number here on the left, then equate that to y. So y is equal to 0 is the horizontal asymptote of this, okay? And this is 2, just look at it, so y is equal to 2. So this is a line that will never be touched by the graph, okay? This is negative 3, and then y is equal to negative 3. Therefore, if we have a function f of x is equal to a raised to x, whether you add or subtract any number c, then the range will follow. If you add c here, then it means to say you start from adding c will give you a range that is positive c to infinity. That is a positive value. Subtracting c will give you negative c, then it goes to positive infinity. Okay? That is how we generalize the behavior of this graph. So what will happen if from base that is 1/2, which is between 0 to 1, that is the first case, what if I have a base that is greater than 1? So let's try to observe. So what if we are going to have a base that is greater than 1? Let's say that is f of x is equal to 2 raised to x, just to give you a reflection of 1/2 raised to x, okay? So when x is 0, that remains to be 1, because 2 raised to 0 is simply 1, okay? 2 raised to negative 1 will give us 1/2. So 2 raised to negative 2 will give us 1/4, okay? So here, 2 raised to 1 is 2, and 2 raised to 2 is 4. Observing that when I increase the values of x here, as observed, that is increasing. The values of y does do the same. They also increase. However, if I decrease values of y here, or of x, the values of y here approaches 0. It is still true that y, or f of x, is equal to 2 raised to x will never be 0 and will never be, a negative number. Let us now graph f of x that is equal to 2 raised to x, and for us to have a different representation, I will name it as g of x, okay? For them not to be the same in the representation. So when x is 0, there you go, y is still 1. When x is negative 1, y is 1/2, so you have here. When x is negative 2, and that is 1/4. Okay? When x is 1, it will give you y that is 2. And when x is 2, y is 4. I am now connecting the points, and you see the behavior. Y here will never be 0 for function g. So I'll connect this also. The graph is a curve, and when you try to observe the graph of function f and the graph of function g, they are reflections of each other, okay? Meaning to say, if we also observe how the function g behaves, when x keeps on increasing here, when x keeps on increasing, y also does the same. It also increases. Okay? Now, when x decreases here, y gets closer and closer to 0. It will never be 0. Okay? Now, there exists also a horizontal asymptote. They have the same horizontal asymptote, y is equal to 0. Domain is also the set of all real numbers, and that's not a question already. Range of this function g, the range of function g, that will be all numbers greater than 0. They have the same range because they have the same behavior. They both increase, these two. Okay? They also have the same domain and they have the same horizontal asymptote. Only that their difference is the behavior. That when x keeps on increasing here, y keeps on increasing. But the other, when x decreases, you see it's decreasing here, y increases. So they have a different behavior on that case. Now let us complete the table. We have the functions here, wherein the base is greater than 1, that is the second case. So g of x is equal to 2 raised to x has a range all numbers greater than 0. And this is 0, observe 0 as the number which is excluded. Okay, that is a excluded number. Then y equals 0 will be the horizontal asymptote of that. Okay, so here you see this is 4, exclude 4. So the numbers greater than 4 are all part of the range. Now here, y is equal to 4. Just need to observe this 4. Okay, now negative 7. So the range of this function 2 raised to x minus 7 is a set of all real numbers greater than negative 7. So here, y is equal to negative 7. So the excluded numbers here will be in equation, equate that to y, and this will serve as a horizontal asymptote. Now observe that if we have a negative sign here, we have negative 2 raised to x. Remember, negative is not part of the entire base. Okay? Now, if there is a negative sign that will exist here, it means to say the number, all numbers y will never be a positive number because it is now controlled by a negative here. Okay? Now, if I release or exclude negative sign here, we have 2 raised to x. It means to say function h is a reflection of function g. That is, its graph will now be like this. When x is 0, we have, so when x is 0, y is 1. When x is 1, this will now be negative 2. When x is 2, negative 4. You see what is changing? When x is negative 1, we have negative 1/2. X is negative 2, we have negative 1/4. Meaning to say, there will be no, okay, this must be negative 1 because of this negative sign. Okay, there will be no positive real value of y. Meaning to say, the graph will look this way. So reflection of this blue graph here. So this is 1/2, 1/4. This is 2. So this will give us negative 2, negative 4. So here. So here, observing the graph of function h, it is a reflection of function g. You see, if you try to fold this x and y plane, then it seems like they're reflecting each other, a mirror image, okay? So, when x here keeps on decreasing, as observed on the movement of the graph, the value of y gets closer and closer to 0, you see. So, meaning to say, this y equals 0 remains to be a horizontal asymptote. But when x keeps on increasing, what's happening here as observed? Y keeps on decreasing. You see the movement, the path of this curve? It decreases, the y decreases. okay, while x increases. That's why it's already found in this part. So what is the implication of this graph? So the range of function h here, range of function h will now be, it decreases. As observed, it is decreasing. The y values decreases. So the y values decrease, and it will be all negative real numbers. So it means to say all real numbers less than 0 is the set of y values, or the range here. But the reflection of this function f of x is equal to 1/2 raised to x will be, let's name that as function p. P of x is equal, just place negative sign, so negative 1/2 raised to x. Okay, so that is a reflection, so it will look this way. When x is 1, it will give you 1/2. When x is 2, a negative 1/2. When x is 2, negative 1/4. So it will be like this. When x is negative 1, it gives you negative 2. When x is negative 2, y is negative 4. This will be the graph of function p. Meaning to say, the range of function p is the set of all real numbers less than 0. Okay? However, if we try to observe the behavior of the graph function p, when x keeps on increasing, y gets closer and closer to 0. You see the movement here. It increases, y increases here, but x increases here, but y gets closer and closer to 0. But in here, x keeps on decreasing here, but y does the same. It also keeps on decreasing. So you see, these are just representations of the graph of the possibilities. It means to say also that if you have a function f of x is equal to negative a raised to x, remember this negative sign is not part of the base a, okay? Plus or minus c, then it means to say this negative sign will automatically tell you that all values of y decreases. And when all values of y keeps on decreasing, so you need to observe here positive x. So when that is plus any real number c, then you have all numbers less than c. It means to say all numbers less than c here. Okay, but when you have negative real numbers, so you have negative c. So here y is less than negative c. So if I place negative sign here, negative, negative, all of this function, I place negative here, range will change. Why? Because it means to say that the values of g, the values of f, or f of x and g of x will now keep on decreasing. So all of them will decrease. So I have negative infinity, this is 0. And so this one, all numbers less than 2. All numbers less than negative 3. All numbers less than 0. Here also we have all numbers less than 4. All numbers less than negative 7. You see, that is the power of this negative sign. And it will always decrease. The horizontal asymptotes will not change. Those remains to be aligned regardless of decreasing or increasing values of y. As observed here, even though you increase or you decrease, since you have the same representation a raised to x or negative a raised to x, then y equals 0 remains to be the horizontal asymptote. That is the idea there, okay? But if you add, if you subtract, then there is a change in the horizontal asymptote already. It's like this. If you add c, then y equals c will be the horizontal asymptote. Minus c, then y equals negative c is the horizontal asymptote. And these are some of the properties of exponential functions.